Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistance, and today we are looking at intermolecular forces. We're asked to list the types of intermolecular forces that exist between any given pair of molecules. And in so doing, we want to recognize that intermolecular forces occur between molecules rather than inside of molecules. There are intramolecular forces, which are forces that occur within the molecule, and there are intermolecular forces that occur between two different molecules. Those two different molecules can be the same type of molecule. They could both be methane, or they could both be water, but it has to be between two separate molecules. So let's take a look. We've got HF and H2O. HF is a polar molecule, as is H2O. We can even draw these out. Hydrogen fluoride. Fluorine is very electronegative. So our dipole moment would be toward fluorine. And then, of course, we have a resulting dipole in oxygen. The resulting dipole goes that way, as oxygen is more electronegative than hydrogen is. So, knowing that we have two instances where we're going to have these dipoles, we can say that we're going to have dipole-dipole, which is a specific type of intermolecular force. Every single molecule, as they relate to one another, the intermolecular force will generally have dispersion forces. Regardless of whether they're polar or non-polar. And you can look at this as a sort of induced dipole type of force. And then the last thing that we want to look at is that we can have some measure of hydrogen bonding. And we know that because hydrogen bonding can occur between hydrogen and either oxygen, nitrogen, or fluorine. And you can kind of think about it like the hydrogen is creating this little dashed intermolecular bond with the fluorine. And it's kind of holding the fluorine a little tighter than it would if they were just dipole-dipole and dispersion forces, but not quite as tight as if they were on the same molecule. Similarly, the hydrogen over here could be, depending on its position, creating a hydrogen bond with the oxygen in water. So, having said all that, just write that down, hydrogen bonding. That's a special type of bonding that only occurs between hydrogen of one molecule and either the fluorine, oxygen, or nitrogen of another molecule. Okay, so that's our first pair. Our second pair is the diatomic bromine and carbon tetrachloride. So for this, we can look at it in terms of, let's draw carbon tetrachloride first. You've got carbon, and then you'll have a chlorine that's sticking out. And generally when we do that, we do this sort of wedge shape. And then you're going to have a chlorine here, and a chlorine there, and one more up above. And each of the chlorines has 3 lone pairs on them. And you'll probably already note that because of the spacing between the different atoms in this molecule, all being equidistant from one another, that their respective dipoles will cancel each other out, making this a nonpolar molecule, despite the fact that it's pulling. Despite the fact that you have these sort of dipoles, you do not have a dipole moment. There's no net change. There's no net dipole. So with all of these canceling each other out, this would be a nonpolar molecule. Similarly, whenever you have a diatomic molecule, you have bromine attached to bromine, and they each have 3 lone pairs because they're halogens. This is a nonpolar molecule in its very basic sense. There's no resultant dipole because they have the same electronegativity. In fact, there's no dipole at all for all intents and purposes. So the only force that we're dealing with here are dispersion forces. And they can be things like induced dipole, also called van der Waals forces. They're known by multiple things, but for the purposes of this text, we're going to call them dispersion forces. Okay, moving right along. We have another diatomic, which is fluorine. Diatomic fluorine. That's going to be nonpolar, just like diatomic bromine was. And then we have we also have thiocyanate ion. So that is actually an ion. You can see the little negative charge on it. It's difficult to see, but it's there right next to the nitrogen. So we have an ion and we have a nonpolar molecule. Well, whenever you have an ion, you know that you're going to, along with another molecule, you know you're going to have an ion-induced dipole forces, which are rarely talked about, but they do exist. So it's creating this sort of dipole for all intents and purposes. It's creating this little bit of dipole between the diatomic fluorine and the thiocyanate just by virtue of the ionic character of the thiocyanate. And we would also have dispersion forces because those exist between all molecules. And again, you can call dispersion forces van der Waals forces if that helps, or induced dipole forces. That's a little more descriptive. But again, we're just going to refer to them as dispersion forces. So the last one we have is pH3 and C4H8. So pH3 is going to look like this. And recall that phosphorus should have a total of 5 valence electrons, so it does have this lone pair. And if we were to write out our dipoles, it's going from hydrogen over to phosphorus, but you have these lone pair pulling it this way. So the resulting dipole is going to be in this direction. That's our resulting dipole. Okay. And then C4H8 is a cyclobutane. It looks kind of like a diamond. And you can even draw out the little hydrogens if you'd like. And when drawing out hydrocarbons, generally, it's understood at the angles, at these little corners of the diamond, is actually a carbon. So each of those corners is just a carbon. That's all it is. And so what we know from hydrocarbons is that they are nonpolar in nature. If you were to draw all the little dipoles that result in this hydrocarbon, you would note that they all cancel out. And it's also interesting to note that the difference between electronegativity between carbon and hydrogen is not that significant. So ultimately, you're dealing with a nonpolar molecule. So we have a polar molecule with a nonpolar molecule. So because we have this polar with nonpolar, we're going to have dipole, induced dipole. Forces. And of course, we're also going to have dispersion forces. Okay. So, rapid fire, we can take a look and see which of the following can form hydrogen bonds with water. Recall that hydrogen bonds can only form between a hydrogen and either a fluorine, so we've got fluorine, oxygen, or nitrogen. So going down the list, all we have to do is identify, do we have oxygen, do we have fluorine, do we have nitrogen? Although there is a trick in this. So our first one is an obvious yes. Our second one is the trick one, because if you have this ethane, which is C2H6, and it's near water. Now remember, water has the oxygen already. Ethane is supplying the hydrogen this time. So yes, it can form hydrogen bonds with water, as can diatomic fluorine, as can our second to last option. And the only one in this list that cannot is our potassium ion. So when looking at this, you might be tempted to think that all molecules can form hydrogen bonds, but it's important to remember that you have to either, one of the molecules has to have a hydrogen and the other molecule has to have one of these three: fluorine, oxygen, or nitrogen. So if we had done something like forming hydrogen bonds with methane, let's go ahead and do that real quick. Let's change this to methane. And methane's formula is CH4. So the same would be true. We can go ahead and say that yes, this would be true. This would not be true, because all you're dealing with is hydrogens and carbons. There are no fluorines, oxygens, or nitrogens. But our third option is correct, as would our fourth and fifth. So the only one that would change in this case is the ethane. Ethane and methane do not form hydrogen bonds with one another. So that's a little something to recognize when looking at whether or not you have hydrogen bonds, is that one molecule has a hydrogen and the other has fluorine, oxygen, or nitrogen.